Theorem 5.15 says that if we have metrics d and d prime on a set X, which induce topologies t and t prime, then topology t prime is finer than the topology t if and only if for every point in the set and every epsilon greater than 0. If you look at the ball of radius epsilon about x in the d metric, you can find an open ball from the d prime metric which is centered at x and which fits inside this epsilon ball. Okay, you can find a delta that makes that work. So the sort of d prime balls fit inside the d balls, basically. All right, so exercise 5.27, consider the metric d sub v on the plane defined by distance from point P to Q is 1 if the first coordinates are different, or if they're the same, but the second coordinates are at least 1 apart. And okay, in the opposite case, if the first coordinates are different, so the points are sort of above and below one another, and the second coordinates differ by less than 1, then we're going to let the distance be, well, I guess that would be the normal Euclidean distance, right? In this case, just the distance between the second coordinates. All right, so part A, use this theorem to prove that topology induced by d sub v is finer than the standard topology. Okay, well, what do the open balls look like in this, with respect to this metric? Picked a point P here in the plane, and the open ball of radius 1. Well, that consists of all the points that are at a distance less than 1 from P. So basically, we don't want this first case, but we want anything in the second case, right? Because this distance here is always going to be less than 1. So we want all the points with the same first coordinate as P, P1, and such that the second coordinates differ by less than 1. So basically we can travel up or down by any amount less than 1. Okay, we get a little vertical interval. Now if I increase the radius just a tiny bit, I could add a few more zeros in here if I wanted to. Now I want everything with radius, everything with distance from P less than this number, and well, the distance is always less than that number, right? Distance is always less than or equal to 1 for this metric. So every point is in this ball. Okay, we get the entire plane. So a small, tiny little change in the radius can have a big difference in how big the open ball is. All right, so if we're going to prove that this is finer than, that the topology induced by this metric is finer than the standard topology, then, okay, let T be the standard topology induced by the standard metric D. Let T sub V be the topology induced by this new metric D sub V. And we have to take any sort of epsilon ball in the standard metric and find a delta ball with respect to the D sub V metric, which will fit inside of it. Okay. So taking a little sort of open ball, right? And well, this thing's not going to fit inside of it, so we're going to need to find a little interval that fits inside of it. And I guess we should be able to take delta to be the same thing as epsilon, unless epsilon was bigger than 1, right? And then we're going to get this if we let them be equal. So delta needs to be smaller than epsilon. It also needs to be no bigger than 1. Okay. So how about given a point in epsilon, we let delta equal the minimum of epsilon and 1. That should do it. Okay, so we're going to show that, I already wrote that up here. We're going to show that this ball is contained in that one. Okay, so suppose that we have an element y in this allegedly smaller ball. Y is in, copy that. Okay. So that, what does that mean? The distance d sub v from x to y is less than delta, right? Okay. Well, since we have chosen delta to be certainly less than or equal to 1, we have, okay, the distance is actually less than 1, right? So it's the second case here. In particular, the distance from P to, well, from x to y is given by this formula right here. Okay. Distance from x to y is, I'm sorry, lost my place. Try again. We have that, yeah, we're in this case, so x1 is equal to y1. And as I mentioned, the distance d sub v from x to y is equal to just the distance between the second coordinates. Good. Okay. Well, I need to show that y is contained in this open ball in the standard metric, so I need to show that the distance d of xy is less than epsilon. Okay, so let's try and calculate that. D of xy, standard metric, by definition is the square root of x1 minus y1 squared plus x2 minus y2 squared. And we've just said that x1 is equal to y1. So this difference here is 0. So all we're left with is the square root of the square of x2 minus y2. And that's the same thing as the absolute value, x2 minus y2. And okay, we've said right here that that is equal to d sub v from x to y. And, well, that's less than delta since y is in this delta ball. Okay, and we've chosen delta to not only be less than or equal to 1, but to be less than or equal to epsilon as well. So there you have it. The distance from x to y is less than epsilon. So we can conclude that y is in this epsilon ball about x with respect to the standard metric. And that does it. This proves that we have this inclusion. Right? So the topology T sub v is finer than the standard topology T by our theorem 5.15 up here at the top. Okay, so it's finer. That leaves open the question of whether it's strictly finer or actually equal. And well, these open balls really do seem smaller, right? I don't think we can fit our standard open balls inside of those small ones. So it must be strictly finer. In fact, I suspect that this metric actually induces the vertical interval topology on R2. You can think about that. All right, so let's try to show that the topology induced by d sub v is indeed strictly finer than the standard topology. And there's my picture. So let's observe that the open ball be respect to this metric about the origin of radius 1, which is what I've tried to draw here, this vertical interval. Well, what is that? It should be the set of all points 0, y, right? It has to have the same first coordinate, and then the second coordinate has to be a distance right, less than 1 away from 0. So in other words, it's just 0 times open interval from -1 to 1. Okay. This open ball is a basis element, in the topology T sub v. Try again. Sub v. Okay, well, suppose for contradiction that this set is open in the standard topology. Okay. I want to prove that it's not, that I have an open ball, or in particular an open set in the T sub v topology, which is not open in the standard topology. Okay. So suppose it is, and let's get a contradiction. All right, well, then if it's open, then by the local criterion, we must be able to find some open ball in the standard topology about the origin, which is contained in this vertical interval, which sounds ridiculous, but let's see why. So there must exist some open ball with respect to the standard metric about the origin, some radius epsilon, some such ball with respect to the standard metric D, which is contained in our other open ball up here in the other metric, 0 times -1 to 1. All right, but I mean, look at the picture. That ball, it contains a bunch of points that are not on the vertical axis, right? That have first coordinates that are not equal to 0. So in particular, this ball contains the point about epsilon over 2, 0, which is not in the set 0 times -1 to 1. Okay, so that's our contradiction. We can't have such an open ball contained inside of this open ball up here. All right, so we've shown that there are some sets that are open in T sub v, but not open in the standard topology.